Hi everybody, it's Miss Black again, and we are now in section 5.5 of Identities. We've already learned about our 11 fundamental identities that we need to memorize and seen how to use them. We worked on in 5.3 and 5.4 the sum and difference identities, and even though we don't have to memorize them, we understand there was a purpose for them, that they helped us evaluate trig functions of angles that we could not look up on the unit circle or on our special right triangles. In 5.5, we're going to continue. We have another group of identities that we're going to have to learn how to use. They are called double angle identities, and their name is exactly what it's talking about. The angle is going to be doubled. So when we think about doubling, what operation are we talking about? So think, if we double 3, we get 6. That really means we took 3 and multiplied it by 2. So a double angle identity is not going to be where the angle's A or B or just theta. It's going to be 2A or 2 theta or 2B. It's going to be doubled. And if you look, we have a double angle identities for sine, cosine, and tangent. And again, you do not need to memorize these. We just need to know how to use them. Now, unlike in section 5.3 and 5.4 where I did not show you where those sum and difference identities came from, I just said, hey, the proof is in the book. These are easy to prove, so I'm going to prove to you one of them, where it comes from. And the one I'm going to prove for you is where do we get the trig identity cosine 2a. And it goes directly related to those identities we just learned in 5.3 or 5.4. So if you remember, we learned the sum identity in 5.3 for cosine A plus B. So in 5.3 we had the identity. If you had angle A plus angle B and you want to find the cosine value of that, we couldn't distribute the word cos. Instead, it really equals cosine A, cosine B, minus sine A, sine B. Everybody's with me? When we use the variables A and B, that is implying that angle A and angle B are not the same size. But guys, what happens if they were? What happens if you were doing a sum of two angles and the angles were exactly the same? Would you have to call them A and B? No. If they were exactly the same size, you could call them both A's. And that's what I'm going to do. I'm going to call both of these angles big A. Well, what that does is, when I rewrite the identity, what it equals, I'll use just the big A for all the angles. All right, what that happens then is if you look, A plus A in algebra is really 2A, hence a double angle. A is doubled. On the right side, cosine A times cosine A, we can multiply because there's an angle behind that trig function. There's an angle behind that trig function. So cosine A times cosine A is cosine squared A, just like x times x is x squared. Sine A times sine A is sine squared A. Hence, that's where we get the double angle identity. Everybody see it? Now, the first thing I want you to notice, be very careful. This is not the Pythagorean identity. It looks like it, but it's not. The Pythagorean identity from section 5.1 was sine squared theta plus cosine squared theta equals 1. Those two trig functions squared were added. This is subtracted, which means it matters. Cosine squared minus sine squared have to be in that order. The cosine's got to be positive, the sine's got to be negative to be this double angle. Now, you're going to look and say, well, why for cosine, for a double angle, are there really 3 statements, 3 different identities? Because you can use the Pythagorean identity to get this and manipulate it. Remember, the Pythagorean identity is sine squared theta plus cosine squared theta equals 1, correct? That was the Pythagorean from section 5.1. Well, guys, if I just wanted to know what cosine squared is, couldn't I move the sine squared by subtracting? Well, if this statement says cosine squared theta is 1 minus sine squared theta, that means over here I could do a substitution. I can replace cosine squared A with 1 minus sine squared A. So now I have 1 minus sine squared A minus sine squared A. These are like terms. They're both negative. So if I add a negative sine squared a with a negative sine squared a, that's where the negative 2 sine squared a is coming from. And just vice versa. Suppose I take the Pythagorean identity and I replace the sine squared a. Well, if this is your Pythagorean identity, if I want to know what sine squared a is, I would move over the cosine squared a by subtracting. So this would be 1 minus cosine squared a. Now, watch what happens. There's a negative sign in front of this. So when I have that negative, it's going to go to both. So a negative times a 1, there's the negative 1. A negative times a negative makes a positive cosine squared, and a positive cosine squared a and another positive cosine squared a gives us the 2 cosine squared a. So I did want you to see that these identities are not just falling out of the sky on somebody's paper. They are developed from one to the other. Again, you don't have to memorize them. You have to learn how to use them. So in your notes, let's go to example 1a and understand what was the purpose of these. Okay, so here I am, I'm in school, and I'm asked to look up the value of 2 cosine squared 15 degrees minus 1. And I cannot have a calculator because they didn't exist. Well, we all know 15 degrees is not on the unit circle. 15 degrees is not on our triangles. How do we look this up? We notice that this is one of these identities. We only have one angle in this expression, and it's 15 degrees. I'm going to label that as A. So if you look, I have 2 cosine squared A minus 1. 2 cosine squared A minus 1. I have this right side of the identity. Well, I know this equals cosine 2A. So I know this statement is equal to cosine 2A. So now let's fill it in. This is cosine 2. Angle A is 15 degrees. Hey, 2 times 15 degrees is 30 degrees. That I can look up. Because I know I could draw a 30-degree triangle in quadrant 1. I know the side opposite the 30 is 1. The hypotenuse is 2. That makes the other side square root of 3. I know the definition of cosine is x over r, or adjacent over hypotenuse, and that gives me square root of 3 over 2. So the value of 2 cosine squared 15 degrees minus 1 is this value, square root of 3 over 2. And I never needed a calculator. Okay? Let's go in your notes to 1C. Let's look at that one. So 1C says, without a calculator, look up 2 tangent pi over 3 times 1 minus tangent squared pi over 3. Again, I want to look the value of this expression up without a calculator. Well, first of all, if we notice our angles in what units? That's right, it's in radians. So we might as well just change that to degrees. So we know pi is how many degrees? 180. 180 divided by 3 is what? 60. So this is really 2 tangent 60 degrees over 1 minus tangent squared 60 degrees. Now, let's think about this. Can we look up 60 degrees without a calculator? Sure we can. We could use our 60-degree triangle, right? But however, look at the work you have to do. You would have to find out what the tangent of 60 degrees is as a number and multiply it by 2. Then you would have to find out what the tangent of 60 degrees is as a number, square it, and subtract it from this 1. Then you would have to take this number in the numerator and this number in the denominator and divide them. It can be done, it's just a lot of arithmetic. What happens if there was a quicker way? Well, there is. If you look closely here at this expression, we're only dealing with one angle. 60 degrees, 60 degrees. So I'll call that the letter A. This expression right here matches the double angle for tangent. You have 2 tangent A in the numerator and 1 minus tangent squared A in the denominator. So I could replace this cumbersome fraction with this expression. This really equals the tangent of 2A. And that becomes a simple calculation because this is going to be the tangent of 2 times 60 degrees, which is really looking up the tangent of 120 degrees. And then I have no calculation, no dealing with squaring or subtracting or a fraction. But how do we look up the tangent of 120 degrees? Well, we know 120 degrees is in quadrant 2, because we know from here to here, the initial ray to the terminal ray is 120. To use the triangle in quadrant 2, we need the reference angle. If this is 120, this angle must be 60, the reference angle. 180 minus 120 is 60. I know the side opposite 60 is square root of 3. I know the hypotenuse is 2. That length is 1. We're in quadrant 2. We know the x value is negative. Now I can look up the tangent of 120 degrees. Tangent is y over x. The y value is square root of 3. The x value is negative 1. And when I divide that, I get negative square root of 3. So the value of this expression is negative square root of 3. And it was a lot easier to relate this to a double angle and only look up one angle than to do the whole calculation here. Is everybody good so far? All right. Now let's go to a more complicated one. Let's look at example 2 in your notes. Okay, because that's where the fun begins. Okay, example 2 says, use the identities to find the value of sine and cosine for each angle measurement. So in the directions it says to find the sine, I don't know why I wrote the whole word out, to find the sine of 2 theta and the cosine of 2 theta. Okay, that's what they're asking us. Find the value of sine of 2 theta, find the value of cosine 2 theta. And they give us some information. They give us sine theta is 2/5 and cosine theta is less than 0. Now, here's the problem. There's going to be a careless mistake made by you guys. You're going to see, oh, they gave us the value of sine theta. Theta is an angle. We have no idea what size that angle is. We know, because this fraction is positive, this angle is either in quadrant 1 or 2. But I have no clue. Is it 1 degree? Is it 179 degrees? I have no idea how big this angle is. They want the value of doubling that angle. And here's where the boo-boo's going to be. You guys are going to think because they doubled the angle, you just double that value. That is so wrong. That is not what you do. When you see a double angle, it means there's a rule, an identity. So to find the value of sine 2 theta, first we got to pick out the correct identity. So sine 2 theta, now I know, in the book, in the textbook, they use A. A and theta are interchangeable. They represent an angle. If they're using theta in the example, I'm going to use theta in my work. So sine 2 theta is 2 sine theta cosine theta. If I can fill this right side of this identity in, I will have my answer. So I know sine theta because it's given here. Even though I don't know how many degrees that angle is, I know what the trig function value is. The sine of theta is 2/5. I got that. I need cosine theta. Well, they don't give me cosine theta. All they say is cosine theta is less than 0. So let's think. Let's go back to the beginning of the semester. Trig is a relationship between an acute angle and a right triangle and 2 sides. Your acute angle is theta. These are your 2 sides. You must need to draw a right triangle. Okay, so we're going to draw a right triangle. But which quadrant do we put it in? Do we pick? No. Again, we know the sine value is positive 2/5. That tells us our triangle is either quadrant 1 or 2. But it matters which quadrant. So what's this information telling us? If cosine theta is less than 0, anything less than 0 is negative. And now we can make a decision. Where is sine positive but cosine negative? That would be in quadrant 2. So here's our triangle in quadrant 2. Here's our theta. The sine is y over r. So now we got to get side x. So can we use Pythagorean theorem, or do we have a special right triangle? Is it a triple? It is not a triple. It is not 3, 4, 5, because you see a 5. That's not a 3. And it's not 5, 12, 13, because in order to use the triple 5, 12, 13, the 5 would have to be one of the legs. So we're going to have to do Pythagorean theorem. So x squared plus 2 squared equals 5 squared. X squared plus 4 equals 25. I subtract 4, I get 21. I take the square root of both sides. I always get 2 solutions. I cannot break down the square root of 21 because it's prime. Well, the factors of it are prime. The factors are 7 and 3. There's no perfect square in 21. The x value can't be both positive and negative. In quadrant 2, the x value is negative. Now I have a drawing, and I can use my drawing like I did in chapter 1 to find the cosine value. Cosine is x over r, or adjacent over hypotenuse. Now this becomes simple arithmetic. We are multiplying fractions is no problem. Top times top and bottom times bottom. This is 2 over 1. 2 times 2 is 4. 4 times a negative is negative 4. Negative 4 times square root of 21 is negative 4 square roots of 21. The denominator is 1 times 5, which is 25. Now let's think about this. If we know theta is in quadrant 2, that means that angle is bigger than 90 and less than 180. So it's between 90 and 180. If you double that, would the triangle still be in quadrant 2? Well, no, if you double 90, you'd be at 180. And if you double 180, you'd be at 360. So when you double this angle, that triangle is now either in 3 or 4. That's why this value is now negative. Okay, but we're not done. Now it asks you to do the cosine of 2 theta. So, cosine of 2 theta. Again, I look at this expression and I see it's a double angle. Again, that does not mean you just take the cosine value and double it. You have to go find the identity. The problem with the cosine double angle identities, there's 3 to choose from. It doesn't matter which one you choose, but I like to do the least amount of work. I do not want to work with this square root again. So I don't want to work with cosine theta again. I'd rather work with sine theta because it has 2/5. It has a nice fraction. So if you look at it, these 3 choices for the double angle for cosine, I will pick the second one because all I have to do is deal with the sine. So I'll write it out. Cosine 2 theta is 1 minus 2 sine squared theta. I'm going to do my substitution. I'm going to replace sine theta with what it equals, 2/5. But hey, look, there's a square on that. So that means this fraction is going to have to be squared. I'm going to follow order of operations. I don't subtract first. I don't multiply by 2 first. I square first. Top times top is 4. Bottom times bottom is 25. I'm going to follow order of operations. I can't subtract because I got to multiply. So this is 1 minus 2 times 4/25 is 8/25. To subtract, I need a common denominator, which would be 25. So this would be 25/25 minus 8/25, which is 17/25. You found, without actually knowing the actual measure of angle theta, you know if you doubled it and found the cosine value, that it would be 17 over 25. Now think about this. Let's see if we can figure out in our head where 2 theta is now. If theta is an angle between 90 and 180, correct? Because it's in quadrant 2. If you double 90, you'd be at 180. If you double 180, you'd be at 360. So when I double these angles, the triangle's either in quadrant 3 or 4. Well, you know the sine double angle value is negative, but the cosine double angle is positive. So what quadrant would that be? Would that be quadrant 3 or quadrant 4? Very good. I know without even knowing actually theta, if I double theta, I'll be in quadrant 4 because cosine is still positive, sine is negative. All right, let's look at example 3 in your notes. I'm going to try one more with these because this one, again, requires some more work, and I want to make sure you understand it. Okay, so let's look at 3b. There's another example. All right, this says, find sine and cosine of theta. So on 3b, the question is asking us to find the sine of theta and the cosine of theta. It says find theta. So it's not asking us to find the double angle anymore, it's just asking us to find the regular angle. And we're given cosine 2 theta is negative 5/12. And we're given theta is in between pi over 2 and pi. All right, so this is a little bit more complicated because they're not giving us the theta value, just the angle to substitute in and get the double. They're giving us the double and they want the original. All right, so if they're giving us the double angle of cosine and they want us to find sine, which of these identities would we work with? If we're given a double angle for cosine and we want to find sine, we need to pick choice, the first choice or the second choice, because they both have sine in them. But would you want to pick the first choice that has cosine and sine, two unknowns, or this one that just has one unknown? Correct. So if I have cosine 2 theta, I know the left side. I know what this equals. I want to find sine. I want to use this middle identity because I just want to find this one unknown. So I'm going to write that down. Cosine 2 theta equals 1 minus 2 sine squared theta. Correct? We know this. We're given it. It's negative 5/12. It equals 1 minus 2 sine squared theta. We are getting a good taste now of solving a trig equation. Even though we haven't formally been introduced, guys, this is your unknown, sine theta. We want to solve for it. Solve means to get it isolated. So to get this expression by itself, we have to move the 1 and we have to move the negative 2. How do you move numbers across equations? You do the opposite operation. So this one is connected by addition. There's a plus, so we would move it by minusing it. Now, to subtract fractions, you need a common denominator. Negative 5/12 and negative 1 have the common denominator 12. And if you change the denominator, you change the numerator. So do you all agree negative 1 is really written as negative 12/12? And a negative 5/12 and a negative 12/12 would make negative 17 over 12. I move the 1, so this is what I have now. Negative 2 sine squared theta. But I still have another number to move, negative 2. It's connected by multiplication, so I move it by doing division, right? But we know in fraction land, there's no such thing as dividing fractions. We multiply by the reciprocal. So the reciprocal in negative 2 is really negative 1/2. And what happens, a negative times a negative makes a positive. That becomes 17 over 2 times 12, which is 24. Now, that's not what they want. They don't want to know what sine squared theta is. They want to know the value of sine theta. So just like you learned in arithmetic, how do you get rid of a square? The same way you do it for Pythagorean theorem. You square root both sides. What do squares and square roots do? They're opposite or inverse operations. They cancel out. There's your sine theta. When you square root a fraction, you're square rooting both the numerator and the denominator. And there's always two answers when you square root. Are y'all with me? I can't leave that. Let me write it up here. So we have sine theta equals positive and negative square root of 17 over square root of 24. If you're in a square root, you need to reduce. Can we reduce square root of 17? No, it's prime. 24 has a perfect square in it. 24, if you know, is 4 times 6. What's the square root of 4? 2. Okay, so the 6 comes out. The 2 comes out because we did the square root of 4. The 6 stays inside. Can't leave that. Can't leave a radical in the denominator. So we rationalize. We multiply by square root of 6. So we get plus or minus. 17 times 6. They're both inside the square root, so their product would be inside the square root. That would be 102. We know a square root times itself is that number. So square root of 6 times square root of 6 is 6. 6 times 2 is 12. But here's the problem. The sine value can't have both positive and negative. So now we got to decide which one is it. Is it positive or negative? Well, the only way we're going to know if sine is positive or negative is to know what quadrant we were drawn in. So again, here we go. There's a piece of information right here that we haven't used yet. It says angle theta is between pi over 2 and pi. We know that's 90. We know that's 180. If you're between 90 and 180, what quadrant are you in? Quadrant 2. So now we know this answer has got to be positive because sine is positive in quadrant 2. Okay? So everybody pay close attention. We were given the double angle information and we had to come out with the original angle. So all we had to do is set this up like an equation and solve it. Okay? Let's do the second part. Okay, so let me erase this. Again, we found that to be square root of 102 over 12. Now they want us to find the cosine of theta. And again, we're given the double angle. We want to find cosine. So now you have a decision to make. We have 3 identities, 1, 2, and 3. Well, if we're trying to find cosine, obviously we're not going to use the middle one because that has to do with sine. So it's either the first one or the third one. We know what sine theta is. We could use this first one, but do you really want to take that value, that fractional value, and have to square it and work with those numbers? I wouldn't. So I'd use the bottom one. I would say, okay, cosine 2 theta is 2 cosine squared theta minus 1. It's an equation. An identity is an equation. I know what cosine 2 theta is because they gave that to me. I know this value is negative 5/12. All we have to do is solve this. So this time, we're going to move the 1 by it. Adding 1 is adding 12 twelfths. Negative 5 twelfths plus 12 twelfths is 7 twelfths. Now we want to move the 2 by dividing, but by dividing by 2 is like multiplying by the reciprocal, a half. So that would give me 7 over 24 equals cosine squared theta. I don't want cosine squared, I want cosine. So to get rid of a square, I square root. Squares and square roots cancel out. They're opposite inverse operations. I'm square rooting so that I put a plus and a minus. I'm square rooting the 7, and I'm square rooting the 24. Can't leave that because 24 has a perfect square in it. 24 is 4 times 6. So we really know the denominator is 2 square roots of 6. Can't leave that denominator because you got to rationalize. So we multiply by square root of 6. We multiply by square root of 6. And that's where we get square root of 42 over 12. The answer can't be both positive or negative. So again, what quadrant are we in? 2. In quadrant 2, all students, sine is positive, which means cosine is negative. So there was your crash course on how to use double angle identities to evaluate trig expressions. We have one more section to go. Catch you in the next video.